transformers you've heard so much about? How do they work, and should you be using them? We'll talk about all of that today on NLP for Developers. Simply put, transformers are a new family of neural network architecture first proposed in 2017 by Vaswani et al. You may be familiar with other families of neural network architectures like convolutional and recurrent neural networks. Convolutional neural networks work by having a sliding window that moves over an input array and projecting that into a smaller array. These convolutions are then stacked on top of each other. In general, these types of models work best for image data and haven't had quite as much success with natural language data. Recurrent neural networks work by moving over a sequence. At each point in time, they look at both the information available from the current point in the sequence and also information from sequence points before that one. They've had a lot of success with natural language data, but they do have some drawbacks. Two of the biggest drawbacks are that you need to look at each sequence in order, which means there's a limit to how much you can parallelize the processing, breaking apart the beginning and the end of the sequence and then handling those on different machines. As a result, there's a bottleneck in how fast you can train these models. Another drawback of recurrent neural networks is that, in general, it's easier for them to capture relationships between points that are close to each other than it is to capture relationships between points that are very far from each other, say several thousand points in the sequence. Transformers were proposed to help address some of these problems. You may be familiar with the fact that the title of the paper where transformers were proposed is "Attention is All You Need." Attention has been around for a while, and the general idea is that you learn a weight between each input item and each output item. So here you can see the weight between "let's" in the input sequence and each of the words in the output sequence. Self-attention is very similar, but instead of looking at the relationship between items in the input sequence and the output sequence, you look at the relationship between each item in the input sequence and every other item in the input sequence. In the transformer architecture, you do this several times, so each head learns attention relationships independently. This is multi-headed self-attention. The attention is a series of 3 matrices that are combined together, and every value in each of those matrices is learned, so it's initially randomized and then updated over time as the network trains. Overall transformer architecture, as originally proposed, uses a sequence-to-sequence model that has an encoder and a decoder. The encoder takes in the input sequence and transforms it into embeddings, or numeric representations of that input sequence. The decoder takes that embedding, any other additional information, and creates the output sequence. In transformers, the encoder is made up of a number of multi-headed self-attention modules that are stacked on top of each other. The decoder is very similar. How are these used? The main 2 ways where transformers are used is as sequence-to-sequence models and to create embeddings. So they were originally proposed for sequence-to-sequence modeling, specifically machine translation. More recently, however, a series of approaches, including BERT, uses just the encoder to create embeddings that can be used for other tasks. What are some of the benefits of transformers? Probably the biggest benefit of transformers is that if you have access to sufficient compute, they're much faster to train because you don't have that bottleneck of having to do each item in the sequence in order. Another big benefit of transformer architectures is that the attention mechanism ignores order, so it is as easy to detect relationships between very distant items in the sequence as it is to detect relationships between items that are very close to each other. There are drawbacks, however. One of the biggest ones is that they're very memory and compute intensive. They take a lot of compute to train, and they tend to be very large models. Even very small transformer models still have tens of millions of parameters. They're also a relatively young class of models, so we don't necessarily have a good principled understanding of how changing every hyperparameter will change a recurrent neural network model, but because we've been doing them longer, we generally have a better understanding than we do for transformers. In addition, there's some evidence that transformers might work less well for data where there's a hierarchical relationship, so things like parsing. What are some common errors you might run into with transformers? A big one is very early adoption, so using transformers before you need them for your project. Transformers require a lot of data, and if you're trying to train a model without that enormous amount of data, you're probably going to be better off choosing other classes of models. In addition, because they are so large, running out of memory tends to be fairly common while training transformer models, so you need to be very aware of that and allocate your resources appropriately. Finally, because the libraries and toolkit around building and using transformers is still fairly young, you're likely to be the first person to run into a specific problem, and you're likely to have to go to the library author in order to resolve that. If you're interested in learning more, some additional resources, the blog post The Illustrated Transformer by Jay Alamar is really well written. I'd highly recommend it. In addition, if you're interested in learning more about how we use transformers at Rasa for natural language understanding and dialogue tasks, check out this video by Rasa's CTO and co-founder, Alan Nickel. Thanks for joining today. I hope you found this helpful, and I will see you in the next one. Bye!